तो प्रेजेंटेशन राइट्स का क्या होना है?
शायद इसमें लगा कि
आप देते
इस साइड को और जो जिस फैकल्टी का होगा
हाँ
वो उसमें छोड़ के बनाना
नहीं, जैसे बाहर है क्लास
हाँ।
में हमने
तो
वो
यहाँ से मैं प्रेजेंट बना देते हैं जिसको क्लास ले रहा है ना अपने रूम से या
हाँ,
ऑफिस
तो
से।
वो कैसे इंडिकेट आपको बताते हैं पहले?
हाँ कि मैं अपने यहीं से क्लास लूँगा तो मैं यहाँ से उनको बना दूँगा।
तो उस ईमेल में आपका वो सब है
वो
कॉन्टैक्ट?
नहीं उसमें है, हम इसको बोलते हैं सीधे स्क्रीन।
दोबारा नहीं, जैसे मैं मेरा क्लास है।
आप अपने ऑफिस में हैं
हाँ मैं
तो इसमें है ना ये यहाँ पे
मैंने वो उस पर लॉग इन कर लिया आईडी पे।
ये आप यहाँ पे
हाँ, वन ऑफ द मेंबर्स, ठीक है।
ये यहाँ पे आ जाएंगे
हाँ हाँ हाँ
ठीक है ना। तो इसमें जो भी होगा ना
हाँ
मेक में जो मेरे को बनाना पड़ेगा
हाँ हाँ हाँ
तो उससे यहाँ से क्लिक करके वो निशान आता है एरो वाला ये सर।
हाँ
तो मैं एक प्रेजेंटर बना के
हाँ
मैं यहाँ से बोल दूँगा कि सर आप क्लास ले सकते हैं।
हाँ।
तो मैं इसका बन के सर
वो टाइम से करा लिया है ना,
सर
क्या फॉर्म ले आया वो भिजवा देगा उसमें। उसमें कोई ये तो इंस्टीट्यूट के लिए है ना, अलग से ऑनरेरियम थोड़ी देना है इसमें।
नहीं हुआ तो
हाँ
उसमें कुछ नहीं।
हाँ, उसमें कुछ नहीं है। और उसमें एचओडी से फॉरवर्डिंग चाहिए लेटर में।
हाँ सर कर
ठीक है, करके आपको देना है।
नहीं नीचे किसी का आप भिजवा देना
हाँ
आप
नीचे तीन चार खाली है ना, वो कर दिया था बुकिंग। हाँ ऐसा नहीं।
हाँ है, ओके वॉचिंग।
इसको क्या बोला मैं अरे पता नहीं इसमें यार स्क्रीन से कैसे चला गया ये यार ये आना सर भी आए सुदीप से हाँ सुदीप से
फिर उसको राइट क्लिक करके और वो कर सकते हैं। हाँ नहीं नहीं उसको एक बार हाँ मेक
हाँ हेलो सुदीप सर हेलो
सर को मैं मैसेज करता हूँ।
हेलो
ओके सर को अनम्यूट भी करना है। सर कहाँ गया?
नीचे नीचे नीचे
ये तो हो ही नहीं रहा।
Send unmute request.
हाँ अभी हो गया।
Yeah. Am I audible?
यस सर।
Yes, sir. Thanks. Screen sharing?
वो आप करेंगे
Sir,
सर?
at the bottom of the screen you will see a screen sharing option.
सर को ही करना पड़ेगा अपने।
Yeah. But I can't. It's disabled.
So can you try now?
The screen sharing option is disabled. I can't enable it.
Sir, we have made you the organizer. Can you try?
Okay. So if I click on the screen sharing at the bottom,
Okay, okay, okay. कट कर से
ये
नहीं, ऊपर से कट कर से आप जा।
if I click on the screen sharing option, that is not getting enabled.
Let me check, sir. Just a minute. You can share actually from our screen. Okay.
Yeah, I think now.
Yes, now it's possible. It's coming.
Is this okay?
Yes, sir.
Good morning, everybody. Can you see the slides and can you hear me? Am I audible? Please type on the chat box. Okay, great. Thank you, Vincent. I'll take it on from here. I'll
Yes, sir.
call you in case I have any issues.
Yes, sir. Sure.
Thanks a lot. Okay. Good morning, everybody. I'm Sudeep, and I'll be starting with your protein section. So, welcome to AIIMS, and since we are all in a virtual mode, I'll just briefly tell you about myself. I am an additional professor in the Department of Biochemistry. My name is Dr. Sudeep Sen, and we'll be spending a few hours today and the next few days, and we'll be discussing about amino acids and proteins and some of the other topics related with that. So I would like to keep this interactive, so I would encourage you all to use your chat boxes. And in case you have any queries, please type it out in the chat box. That will be the best way to let me know that if I am going too fast or if you need me to repeat any particular topic, right? So should we start? Okay. So today's class is about amino acids. We have 4 classes on proteins, and today afternoon we have a practical on protein fractionation. So I'll just try and talk to you about some basic features about amino acids and proteins. So you have all come through your 10+2, and you have read about amino acids, you have read about proteins right from the very beginning in your school. So what are the important, or what is the importance of proteins in the human body? Can anybody type it out on the chat box? The usefulness or the utility of proteins in the human body. Okay, structural and functional. Somebody said enzymes, basic building blocks, good. Energy source, building blocks, yes. Receptors, very good. You recently had a class with Dr. Shubhradeep and he talked about membranes and you read about receptors. Transporters, very good. Protection, okay. Hormones. So I have the answers coming in thick and fast in the chat box. That's very good. Antibodies, enzymes, blood clotting, very good. Anybody else? Have you left out any important thing? Carriers, yes. Proteins can be carriers of certain substances. Hemoglobin, yes, I was looking for that answer. Hemoglobin, yes, hemoglobin is a very important protein in the body and it helps in transporting oxygen. Osmotic pressure, right? Very good. Elasticity, packing of DNA, okay. Histone proteins, yes. Anything else? Plasma proteins, yes. Dr. Alpana Sharma will be taking that class on plasma proteins. Plasma proteins are extremely important. Neurotransmitters, very good. Contractility, yes. So essentially, I can understand that all of you are aware of most of the important functions of different proteins. So we'll just quickly recapitulate some important functions. And when you finish this class, you should be able to outline the importance of proteins and different functions of proteins in the body. You should be able to identify the composition and structure of amino acids, understand and explain the classification of amino acids, and understand and explain different properties of amino acids. One of the properties which we'll be discussing in detail is buffering property of amino acids, and obviously there are other important properties which will be covered in the next few classes. So coming to what we just recapitulated, I'll just put in some of the important, briefly discuss some of the important functions of proteins. So most of the answers have come in, and I'm just sort of revising or recapitulating what you have just told me. So one is that it's an important structural component of our body, of the cytoskeleton. Very many proteins form cytoskeletal proteins which help in structural support. Most of you have mentioned about enzymes. Most of the enzymes are proteins, and they play a very important role in maintaining the chemical environment and the biochemical environment in the body. A lot of you have also mentioned about the defense mechanism, and you're right. So immunoglobulins are again a variety of proteins which are helpful to maintain the defense mechanism. And a lot of hormones are, as you know, proteins in nature. Some structural proteins which are helpful to allow the human body to have motility. Actin and myosin, you have heard about the muscle proteins. And as I told you that Dr. Shubhadeep must have covered a lot of important receptors present in the cell membrane and the cytoplasm and the nucleus. So receptors also are a very important role played by proteins. Some of you also mentioned about transport proteins, and just to name a few, proteins that help to transfer iron, copper, and other important materials, compounds in the body. And also they play a very important role in storage. So you must have heard about ferritin, and that's a form of storing iron in the body. So when iron is stored in the body, and some of you must be knowing that when there is depletion, these iron stores are called upon, and they help in tiding over conditions where there is iron depletion. And beyond this, there will be iron deficiency anemia, which is again a very important topic which will be covered in physiology as well as in biochemistry. And so ferritin is a very important storage protein which you will be learning about in due course. Respiratory pigments, again you had mentioned about hemoglobin, and there is also cytochrome. So they form an important element of the electron transport chain and help in respiration, energy production. So again, proteins play a very important role in energy production as well as in respiration. And I think some of you also mentioned about proteins being an alternative source of energy. So as you know that when people have starvation or are deprived of the regular food, then after the regular reserves, glycogen reserves are depleted, then after a certain time, proteins are also called upon to act as an alternative source of energy. And there again, proteins play an important role in the body. And obviously, I think it must have already been started, or it must be about to start, that albumin, one of the most important proteins in the body, help in maintaining osmotic pressure. So you have learned about osmosis and how different. So that is why proteins have a very important role to play in maintaining osmotic homeostasis, right? And buffering action. So we'll be learning about buffering action as we go on. So there are so many important roles which proteins play. Now, since you have already covered amino acids and proteins during your school time, I'll just again recapitulate some important points which must be there in your mind, but for our class we can just start by recapitulating. So you you mentioned about proteins or amino acids being the building blocks. So why are they called the building blocks of proteins, or why are amino acids important? Chat box. Why are they called building blocks of protein? Monomer of protein, very good. Yes, monomers. So they essentially help in building the proteins. And what is interesting, or what you already know, but what is very interesting is that despite there being only 20 amino acids, there are hundreds of different types of proteins. So something very similar to the alphabet that you have in the English alphabet, you have 26 alphabets, 26 letters, and with those 26 alphabets, you can actually build up so many different kinds of words with different meanings. You can build up sentences, you can build up paragraphs. So similarly, amino acids, the primary amino acids are only 20. The star on the slide shows that there are some maybe some conditions we'll be discussing, but where we'll be talking about probably the 21st amino acid. But essentially, for all practical purposes, we know that primary amino acids are 20. But at the same time, we just walked through so many different types of proteins, so many different functions of proteins. So these 20 amino acids can help in building up. Yeah, somebody says selenocysteine. We'll be talking about selenocysteine eventually. So for all practical purposes, there are the primary amino acids, which we say are 20. And what I'm trying to bring to the point is that these 20 amino acids help in making up so many different varieties of proteins through permutations and combinations. And what is interesting is that through the genetic code, the nature has devised such a way that there can be so many variations in the sequence of the amino acids and the composition of the proteins. And what is interesting is that different proteins have different functions. So what we'll be also discussing in the next few classes is about protein structure and function. So the structure-function relationship is also very important for you to realize. It's not just that amino acids are building proteins, but that there are different structures, and those different structures are endowed with different functions. Okay? And amino acids are linked to one another by, how are amino acids linked to each other? Chat box. Peptide bonds, very good. Yes, very good. So peptide bonds are responsible for linking one amino acid to the other, and we'll be discussing about peptide bonds also. And these are again covalent bonds, and there are some features, very interesting features of the peptide bond we'll be discussing in due course of time. And so we just talked about how different amino acids are linked to each other to form different types of proteins, different varieties of proteins, different structures, and those structures in turn will have different functions to perform. So that is very interesting, that different proteins, the structures and the composition of different proteins enable them to perform different functions. Okay? So that is something that you should keep in mind, and we'll be talking about that in detail eventually. And some historical perspective, the first amino acid which was discovered was asparagine, and that's a basic amino acid. We'll be talking about asparagine at some point of time. And probably one of the latest amino acids to be discovered in 1938 was threonine. Okay. Now, amino acids are also known as alpha amino acids, because of the presence of an alpha carbon atom, you have again come through your school chemistry classes, which help you to identify the nomenclature in organic chemistry, and you heard about the asymmetric carbon atom and how by virtue of mirror images you can have different stereoisomers. So spatial arrangement of groups allow them, even though they have the same chemical composition, they have because of isomerism, stereoisomerism, they have different properties. So they have different functional properties or different properties, and that is known as stereoisomerism. And enantiomers is something which we'll also be talking about. So because you have already covered that, so I'm just going through something which is school level chemistry, is that because of the presence of an asymmetric carbon atom, the groups which are there attached to the carbon atom are not superimposable. They are not mirror images because of the chiral carbon, and that endows them with different properties, different spatial arrangements, and as a result they also have optical activity. So you have heard about optical activity. Now, can anybody tell me which amino acid does not have optical activity? Glycine. Wow. Good. Why doesn't it have optical activity? Why doesn't glycine have optical activity? Yeah, 2 hydrogens. So very good. So I'll just be taking you to the, I'll skip one slide and take you to the structure of amino acid, and then come back maybe to this slide. So this is the structure of amino acid, and you can see at the center you have the central carbon. This is the asymmetric carbon which we were talking about, and this is the alpha carbon atom which we were talking about. There is an amino group and a carboxyl group attached. So there is an amino group and a carboxyl COOH group attached to this, and the side chain which is described as R. So in glycine, this side chain is again hydrogen, which most of you have mentioned, and because of that it does not have the property of other compounds which we talked about as asymmetric. So the mirror image will be there, and as a result it will not have optical activity. Very correct. A lot of you have mentioned that glycine is an amino acid. Yeah, glycine is an amino acid which does not have optical activity. So again, a few features of amino acids, and because of the stereoisomerism, you have D and L forms, and I hope you remember that capital D and capital L and small d and small l are not the same. So capital D and capital L indicate the configuration of the groups on left and right. D is right and L is left, I think. And small d and small l is how the polarized light is deviated through optical activity, right? And it is interesting to note that most of the amino acids and proteins are exclusively L stereoisomers. The reason for this is probably not known, but it is probably a selection process by which the L forms are preferred. And when you note, there are only probably a very few exceptions which are there in the bacterial cell wall, which are D forms, but most of the amino acids and proteins are the L stereoisomers. Now here again I would like to mention that amino acids can be named, so you know the different types and names, but they have abbreviations. They have a 3-letter abbreviation as well as 1-letter abbreviation. So something like leucine is abbreviated as U, lysine, phenylalanine, proline, and they also have single letters which help in denoting them. These are exclusive letters which are used in protein nomenclature. So you will be coming across this from time to time. Another very interesting thing is that we can classify, I already told you that there are different ways to classify amino acids, and one of the ways is to classify them as essential and non-essential amino acids. So can anybody tell me what you understand by essential and non-essential amino acids? Essential amino acids? Yes. So you have typed that essential amino acids are those which are required by the body, and so essential amino acids have to be supplied by the diet, and non-essential amino acids are the ones which the body can synthesize. So a mnemonic to remember the essential amino acids is, out of the 20, there is a few which are essential amino acids. MAC will fly. So methionine, threonine, tryptophan, valine. So these are all essential amino acids, and then the rest are non-essential. And it's interesting to note that there are 2 amino acids which are semi-essential. So what do you mean by? Yeah, you can use different mnemonics. I'm just giving you one example. There are obviously different mnemonics which different people prefer. But can anybody tell me what do you mean by semi-essential amino acids? So there are arginine and histidine which are semi-essential. Yes? Yes. So somebody gave the right answer. They are synthesized in the body, but in less amounts. So in conditions where you require a lot of proteins, like for example growth periods, or in disease recovery, or in pregnancy where you require large amounts of amino acids, they become essential amino acids. So that is why these 2, arginine and histidine, are semi-essential amino acids. Now we'll be talking about selenosystine and pyrrolysine eventually. There are, again, they are touted to be the 21st and the 22nd amino acid probably, and we'll be coming to them in the last part of today's class. So we have again asparagine and glutamine, which are again they are amides of aspartic acid and glutamic acid. So these are again amino acids which are which can be amidated. And cysteine is another very interesting amino acid which has a thiol group and which can be oxidized, and 2 cysteine can join to form 1 cysteine, which is through a disulfide bond by virtue of the thiol groups joining together. So 2 sulfide groups, SH groups, join together to form a disulfide bond, and thereby forming cysteine. Now again, coming back to the structure of amino acids, you have an amino group, a central carbon, a hydrogen, a side chain, the R group, and the carboxyl group. So this is the basic structure of an amino acid. And when we start the nomenclature, like in organic chemistry, you have carbon atoms being labeled as 1, 2, 3, 4. Here we start from the amino group and go towards the carboxyl end. So the amino terminal to the carboxyl terminal. That is conventional way of naming amino acids in sequence or in direction. Now there are, in different books you will find different ways of classifying amino acids, and one of the very common classifications which can be seen in most books is by virtue of the side chains. So if you see this, essentially all amino acids are similar. The amino group is there, the carboxyl group is there, the hydrogen group is there. What makes them different is the side chain or the R group. So this is the group which makes the different types of amino acids. So based on the different groups which are present on the side chain, they can be classified into different types of amino acids. So if they have aliphatic side chains, if they have hydroxylic groups on side chains, sulfur containing amino acids, methionine, etc., acidic groups, basic groups on the side chains, aromatic rings on the side chains. So this is one way of classifying amino acids. One way which we just discussed a few minutes ago was on the basis of essential and non-essential. So there are again different ways of classifying amino acids. You don't have to memorize all these things, but it's good if you know that these classifications or these types of classifications exist and what is the basis of this classification. Okay? If you have any doubts, please put it there on the chat box. So we'll address those doubts. So I'll move forward. Now, one very interesting thing is that amino acids or proteins are usually colorless. Most of the cases you will find that amino acids do not have any color. So we need some way to visualize them when we go in for quantification or when we go in for purification or things like that, which we will be doing in the afternoon. So you will have to visualize them. It's very difficult to work with something which can't be seen. So to visualize amino acids, the colorless amino acids or the colorless proteins, people have devised ways and means to identify them with different ways. Now, one of the things which was, I think, covered in your biochemistry practical class, the first practical class, is about absorbance, right? So, putting it very simply, if you pass light through a substance, it will transmit some light and it will absorb certain amount of light. You can identify that through absorbance meters and detectors. But what is interesting is that what is transmitted or what is absorbed is characteristic of every compound. So using a spectrophotometer or a colorimeter, you can identify proteins even though they are colorless, or amino acids even though they are colorless, because of the fact that they have a tendency to absorb light at 280 nanometers. Now, why is this so? I'm sorry. So, because most of the proteins have the presence of amino acids tryptophan, tyrosine and phenylalanine, the aromatic amino acids. So, because of the presence of tryptophan, tyrosine and phenylalanine in the proteins or in the the proteins can be identified by a chemical absorbance peak at 280 nanometers. And obviously, anhydrine staining, because there are other amino acids which may not absorb light. So one of the very common ways of visualizing amino acids is anhydrine staining, which will be discussed in detail. In today afternoon by Dr. Astha, and the chemical reaction which occurs to stain amino acids and to make them visible. Okay, so proteins, by virtue of presence of aromatic amino acids in them, are visualized using a spectrophotometer and a chemical fingerprint at 280 nanometers. Its maximum absorbance at 280 nanometers allows them. Yeah, so there is a very good question. So somebody said that do all amino acids show peak at 280 nanometers or only these three? So it has been seen that only these three amino acids have the maximum absorbance at 280 nanometers. So if you use anhydrine staining, you can identify most of the amino acids, but the 280 nanometers absorbance maxima is used to identify proteins, and because of the presence of these amino acids in them, you can identify that a colorless liquid in a test tube is a protein or not. Okay, so does that answer your question? Okay, now this is one of the features of their properties which are used to identify or determine whether a colorless liquid has presence of a protein. Again, a question has come in: what about proteins that don't contain these amino acids? So when you have, generally you have prevalence of these amino acids in protein, these aromatic amino acids in most proteins. So because there are a large number of amino acids in most proteins, there is some presence of amino acids in any of these 3 amino acids in most proteins. But another thing which you might read in some reference books is that peptide bonds have the tendency to absorb light at 190 nanometers. So you can actually identify proteins very accurately. What is the range of wavelength in which all 20 amino acids show maxima? So that's what I'm talking about. So peptide bonds have this ability to absorb light or they have a chemical absorbance maxima at 190 nanometers, and that can be used theoretically, but it's very difficult to generate light at 190 nanometers. So it's not commonly used, but it's again a matter of information. So peptide bonds absorb light at 190 nanometers. Okay, so we go ahead to a very interesting part of amino acids. So these are again some of the things which you will be knowing, but some other things which I'll be discussing, and please ask questions if the things are not clear. So we just talked about different groups in an amino acid. We have the amino group, the carboxyl group, the H, and the side chain, the R group, right? Now, these amino and carboxyl groups which are present in all the amino acids are ionizable groups. So, you see ionizable, they have the ability to give up or take electrons. So, because of this property, they can act as acids. So conventionally, what you have learned during your school chemistry is that there are different definitions of acids and bases, but one of the definitions of acids is that they are proton donors, okay, and bases are proton acceptors. So that is one of the ways to define acids. So you can have electron donors and electron acceptors also. One common base which we will follow is that acids are proton donors and bases are proton acceptors. So that is known. I'm just recapitulating, right? Now, we said that these groups, the amino group and the carboxyl group present on the amino acid, are ionizable groups and have the tendency to give up protons or to accept protons, and thereby they act as acids or bases. And because of this dual nature, amino acids are also known as amphoteric substances or ampholytes. So, because of the fact that amino groups and carboxyl groups present on amino acids are ionizable groups, and they have the ability to give up protons or to accept protons, they act as either acids or bases. And because of this duality in their nature, they are also known as amphoteric substances. Now, some of the side chains. So there are, again, we discussed that there are so many different kinds of side chains. So some of the side chains can also ionize. So the R groups, if they are polar or whether they are non-polar, so again, whether they are hydrophilic or hydrophobic, they have the tendency to act as acids or bases. Okay, so just keep this in mind. This is again a piece of information which I would like you to keep in mind as we'll be discussing about the buffering action of amino acids. So another thing which you probably would have studied in school is about Zwitter ions, right? So do you know what are Zwitter Zwitter ions? Do you remember? No net charge. Good. No net charge. Net charge is 0, right? So again, when we are talking about amino acids and charge groups, whether they are amino groups or carboxyl groups on the side chain which have the ability to ionize, and thereby there will be charge, right? Now, if and when the net charge is 0, that is a Zwitter ion. So the amino acid or the protein can exist as a Zwitter ion, and the pH at which the amino acid exists as a Zwitter ion is the isoelectric pH or the isoelectric point. The reason why I am discussing about this is because it has an application, right? So electrical neutrality will make it, so when the net charge is 0, it will be electrically neutral, right? So when we try to put it in an electric field, it will not have any movement. This is one of the ways which are used to separate amino acids from each other or to separate proteins. It is known as electrophoresis. You might have heard of the term. We'll be talking about that in the probably on Thursday or on next Monday. Or Dr. Asta will be briefly touching upon it in today's afternoon's class, and she'll be talking about different ways to separate. But remember that electrical charge is a property which is utilized to separate amino acids, and because of the fact that there is a pH or a point at which there is no net electric charge, and that will be different for different amino acids or different for different proteins. So you can actually help in separating amino acids from one another or proteins from one another using or taking advantage of this property. Okay, so this is something which you need to keep in mind. We'll again come back to this later. Now, till here, is everything clear? Can we, if you have any questions about Zwitter ions or the ionizable groups or the isoelectric pH, please ask. If not, then we can move ahead. Does anybody have any doubts? Can we move ahead? Okay. So till here everything is clear. Please ask. If you have any questions, if anything is not clear, please just ask. I will repeat whatever is not clear to you. Good. So we'll move ahead. Now, a slightly difficult thing, I would not say difficult, but something which you just need to focus on and concentrate on. So we just said that the ionizable groups COOH and amino groups are there. Please mute yourself. Okay, thank you. So now just concentrate on what I am trying to tell you is that, so this is how you represent amino acids. So there is an H group, there is a carboxyl group, and this is the very simple monocarboxylic amino acid such as alanine or lysine, which I am talking about. So the side chain is not something which we are focusing on. We are just focusing on the amino group and the carboxyl group. Now, these groups, as we said, have the ability to take up protons or to give up protons, and thereby they act as acidic or basic groups. So you also know that the surrounding environment also plays a role in determining the acidic or the basic nature of the groups. So we'll just be discussing about that. So if the environment, look at the extreme left, if the environment is acidic, so there is in the outside environment there is a lot of H plus ions which are present, and because of that these groups act as proton, so they accept those protons and they become fully protonated at very low pH. If the surrounding environment is low pH, there is excess of protons outside, so these groups accept those protons and become fully protonated. Okay, so at low pH the groups become fully protonated and the amino acid has a net positive charge. Is this clear to you? This is the first step. Okay, so the surrounding environment is acidic, has a lot of H plus ions, and by virtue of that the groups take up those H plus, and at low pH, excess H plus concentration in the environment, the amino acid becomes fully protonated and develops a net positive charge. I'm sorry. So now we transition to a neutral, more neutral environment, and as the H plus ion concentration decreases, one of these groups donate H plus. So the carboxyl group donates, gives up the H plus to the environment as the environmental pH changes, and you can see that there is a positively charged group and a negatively charged group. So what we were just talking about, this Zwitter ion, the net charge becomes 0 at the midpoint of titration. So when the pH becomes more neutral, the carboxyl group gives up the H plus, the amino group still retains the H plus, and because of this electrical neutrality, it becomes, the net charge becomes 0. So this is the midpoint of titration. Now as the outside environment changes more, you have more H plus being given up by the amino acid. So the NH3 plus which was there becomes NH2, and the carboxyl group still remains negative. So it's now fully deprotonated at the end point of titration. So as the outside environment becomes more alkaline, the groups, the ionizable groups which we were talking about, the amino group and the carboxyl group, they give up the H plus which was there, and if you notice on the extreme right, you can see that it's fully deprotonated form and the net charge becomes negative. Okay, so at low pH it is a positive net charge, and at high pH, surrounding pH, it becomes a net negative charge. And at the isoelectric point, neutral pH, this isoelectric point varies from amino acid to amino acid. When the net charge is 0, it will become electrically neutral. Okay? Is this clear to all of you? This central diagram which we just discussed, which I just told you about, is this clear to all of you? If you have any doubts or any questions, please ask. Then if not, then we can move forward. So at low pH, the outside surrounding environment, there is a lot of H plus. By virtue of that, the ionizable groups take up that H plus and the net charge becomes positive. The midpoint, when isoelectric point is reached, there is electrical neutrality, so you have net charge is 0, and as the outside environment becomes alkaline, the groups give up the H plus and take up not actually titrating, but there might be conditions in which the outside environment might be acidic or alkaline, and I'm just giving you something which you will understand, that as we titrate or as the pH of the outside environment changes, it has an effect on the charge of the amino acid or the protein. So here we are not talking about the side group, the R group, we are not discussing that at all. I'm just giving you the simplest example of a mono amino group and a mono carboxylic group in an amino acid like alanine or glycine, in which you are just discussing about the ability of the carboxyl group and the amino group to take up electrons or to take up protons and to give up protons, thereby acting as acidic or basic groups. So is that clear? Any questions? If you have not understood this, please ask. Because if you don't understand this, then you will not understand the next thing which we'll be discussing. Is this clear to everybody? I don't see many people saying yes. Okay. Okay. Thank you. Okay. So we'll just move forward. Then we'll take a break after we finish this, and then we'll again resume about protein structure. Okay. So up till here it is clear. So there is at physiological pH, there is some amount of neutrality. So there is electrical neutrality at physiological pH. So the isoelectric pH might vary from amino acid to amino acid, and at a certain point there will be electrical neutrality. Now again, something titrations. Okay, somebody has asked. Titration means reagent is amino acid and addition is base to acid. So we'll be discussing a titration curve in a few minutes. So it will become evident to you. It will become clearer to you. So again, something which we are recapitulating or which we have just discussed is that there is a terminology called as pKa. And what is pK? It is just a pH at which it is dissociated. Okay, so the acid strength or the basic strength is mentioned as pK, and it is the measure of the tendency of a group to give up a proton. Very simply putting it, it is the ability of a group to give up a proton, and that determines the strength of a weak acid or a strong acid. And the net charge on an amino acid is again depends on its pKa of the different functional groups which we just talked about, and also on the pH of the surrounding medium. So not only is the pKa of the ionizable groups important, but the pH of the surrounding medium is also equally important. And isoelectric pH or isoelectric point is the pH between the two pKa groups on either side of the isoelectric species, and you can identify the isoelectric point by checking or by adding up the pKa values of the two groups and dividing it by 2. So here we are just talking about one single amino group and one single carboxyl group. Now this is the simplest case scenario, but as the side chains also come in, some of the side chains also have a tendency to polarize or to ionize and to give up or to take protons. So the side chains also play a role in determining the pH or the electrical neutrality of the amino acid or the protein. Okay, and so this again has to be kept in mind when you are talking about the acidic property or the pH of the amino acid. Okay, now I'm just talking about a simple titration curve. On the y-axis you have the pH, and on the x-axis you have the titration or the NaOH being added, the hydroxyl groups being added slowly. So what you have done in school is titration with NaOH, and as you gradually increase the hydroxyl ion concentration, the pH will increase. Okay, so this is a simple titration curve which we are talking about, and with respect to amino acids. Okay, so now just keep glycine again in mind. So you have the CH2 here, the carboxyl group, the amino group, and as you keep adding the hydroxyl ion, so what we talked about is the net charge on these amino acids. So at acidic pH, what we discussed one slide back, when the environment has a lot of H plus ions, you have the net positive charge by virtue of the NH plus 3. Here COH is electrically not charged, and because it's of the acidic pH, you have a net positive charge. Okay, now as the titration continues, this is something very interesting, is that the carboxyl group, here the carboxyl group is having a buffering capacity. So again, what you have already studied in your 12th standard, 11th and 12th chemistry is that what is buffer? Can anybody just tell me what is buffer? What are buffers? Yes, chat box? Yes, buffers are some things which resist a change in pH. Okay, so in the body, when you are talking about buffers in the body, then again, what is the perspective when you are looking at it from the perspective of doctors? You have to know that there are certain compounds which are there in the body as a safety mechanism to maintain the pH so that it doesn't change. Why is it important for the pH not to change? Because the body is a very complex chemical system in which there are hundreds of enzymes which are acting for different biochemical functions, and if the pH changes, then those enzymes stop acting, right? They have a very narrow window in which they are active. So you have, or the body has to maintain that pH, and proteins or amino acids are helpful in maintaining that pH by virtue of their ionizable groups, whether it is the side chains or whether it is the carboxyl group or the amino group which we are talking about. So here we are deviating slightly from the 11th and 12th chemistry, but the basis is the same. So the carboxyl group which we were talking about has a narrow buffering range in which you will see that the pH is not changing. Okay, this is because of the buffering capacity of the carboxyl group. 2.3 means that the carboxyl group has the buffering range is pKa plus minus 1. Okay, if you remember your Henderson-Hasselbalch equation, the buffering range or the buffering capacity is determined by pKa plus minus 1. So if the pKa of this carboxyl group is 2.3, it will have a buffering capacity of 1.3 to 3.3, right? Now I'm just telling you about the carboxyl group. So you have the buffering capacity of the carboxyl group which exists at a very low pH, and this is a acidic group, so it has a buffering capacity at pKa of 2.3. Then again, when this exceeds the pH, you will see rises steadily till again the buffering capacity of the amino group comes into play, and there at about 9.6. This will again vary from different amino acid to amino acid. You'll see that it's nearly the same for all the amino acids. Even though we are talking about the same carboxyl and the same amino group, it will vary slightly because of certain conditions, because of probably this effect of the side chains or some other conditions, but it is nearly thereabouts, and the buffering capacity of the amino group is about 9.6. So again, the buffering range is 8.6 to 10.6. Okay. So here you have the buffering capacity of the carboxyl group. Here you have the buffering capacity of the amino group, and there you can see that the pH is not changing much. pH is on the y-axis, please note, and you can see that at these points the pH is not changing much. Thereby these groups are acting as buffers, and note that isoelectric point, it is actually not buffering. So the isoelectric point, even though it is electrical neutrality is there because of the net charge being 0, but you see that the buffering is not there at isoelectric pH. So you can actually calculate the isoelectric pH by adding these two, pK1 plus pK2, and then dividing by 2. I'm just talking about the simplest of simple amino acids, and here you will get the isoelectric point as 5.9. Okay. Now we'll be discussing about other amino acids eventually, but if you understand this, then it will be clear. So the isoelectric point is here. So when are these, what is the pH in which it is acting as a buffer? It is about 1.3 to 3.3 and 8.6 to 10.6. Now what is the body pH? Can anybody tell me what is the pH of the body? 7.4. Yeah. Good. So it's 7.35 to 7.36 to 7.42, that is the range. So if you note that the buffering capacity of glycine is not actually there at the pH of the body, it's acting as a buffer at a much higher and a much lower pH range. So glycine is not a good buffer at body pH. Okay. So now just focus on the right panel. You have glycine, which has two regions of buffering power. It's not a good buffer at body pH, and it has a net negative charge at any pH. So this is what we talked about. So as the pH increases, the charge changes from +1 to -1, and it has a pH net positive charge at low pH, at a pH which is below the isoelectric point, and a net negative charge as the pH increases. Okay. Now all diprotic acids, single amino, single carboxyl group will have similar titration curves. Now why did I stress upon this, that glycine is not a good buffer at body pH? So what we talked about initially is that we need something to buffer at body pH. So here we have histidine, which has, in addition to the amino group and the carboxyl group, there is also the imidazole side chain which comes into play, and because of that side chain, you have the pK of that side chain coming into play, and that pK has a pH of about 6. So because of that, it can have buffering action at from 5 to 7. So that is buffering at body pH or near the body pH, not something which is very low or very high. So here again you can see that the pK of the carboxyl group and the pK of the amino group have changed slightly from what it was in glycine. But what I would like to draw your attention to is that histidine has a buffering capacity at body pH by virtue of its imidazole side chain. Okay, we said that buffering capacity is pK plus minus 1 and the imidazole side chain has the pK of 6 by virtue of which histidine, yeah I know 6 plus 1 is 7, but the range, so generally you need buffering in that range, and that buffering capacity is very close to body pH, and that is why you will find histidine at a lot of sites which require buffering, enzyme active sites, enzyme catalytic sites. Histidine is there by virtue of its ability to prevent a change in pH from occurring. Okay, pK means pH in the change of language of pH in the language of biochemistry. Okay, so pK again is what we discussed, is that what is pK is the pH at which it is half dissociated. So again, coming back to your Henderson-Hasselbalch equation, if you read what is the definition of pK or pK, it is the ability of a group to act as an acid or a base, and which is measured by the tendency of that group to give up a proton or to accept a proton. Okay, so that is the strength of a group has a weak acid or a strong acid or a weak base or a strong base. So each of these groups, ionizable groups, which we were talking about right from the beginning, you have the carboxyl group, you have the amino group, and you have the side chains, which also have, some of which also have the tendency to ionize, also act as acids and bases, and you can identify how strong they are by their pKa values, and these pKa values will determine whether they have buffering activity at body pH or not. Okay, so this is again something which is slightly difficult to understand. Please read this, and we can also discuss this again on Thursday if it is not clear to you. Okay, so we'll take a 5-minute break, okay, and come back. Can we take a 5-minute break? I'll keep the slide here. Okay, so majority says yes. Okay, I'll also take a water break. You also take a water break. You can just move away from your computer screens for 5 minutes. So please note your watches. We'll be back after 5 minutes. It's a short water break, and we'll continue from where we left off. Okay, yeah, a tea break, but a short tea break. Glycine's buffering action. Okay, I'll move the slide back to glycine's buffering action. Okay, so I'll also take a 5-minute water break. You also take a 5-minute water break, and we'll join back after 5 minutes. Okay, please note your watches. Okay. So you had your water break and I had my small break. So we are back. If anybody has any questions, I would rather encourage everybody to go and read and then come back with questions. So that will be probably a better idea. So we'll take up questions on Thursday. I have a class from 2 to 3. So please go and read and come back and then we'll discuss. But if you have any questions, if you have not understood anything, please put it on the chat box.
Sir, the PI in this case is near to the physiological pH, and at PI the buffering capacity should be less, right? So how histidine helps?
Don't confuse the isoelectric point with the buffering capacity. That is what I told you here. In this case, just note that the PI, when there is the PI, the isoelectric point, there is a sharp change in the pH. So the PI is actually not the buffering range. The PI is just a pH at which there is electrical neutrality, but the buffering is not happening at the PI.
in histidine the PI is 7.6, no? So that is close to the physiological pH.
Yes.
Then actually the buffering capacity is less at PI and greater at PK2 and PKR. Then how are we saying that histidine helps in buffering? Like at 7.4 is physiological pH, at 7.6 is PI in this case, because it would be average of PKR and PK2.
Yes. So again, don't bring in the concept of isoelectric point with the buffering capacity. The buffering capacity is again because of the groups, and if you see the y-axis, you can see that buffering capacity, even in cases of histidine, I told you about vaccine, which is very clear cut, but even in cases of histidine, when there is no change or very relatively less change in pH, you will find that in and around the pK values. It's not happening at the midpoint, right? So what you said is 7.6, but the pKa values are where the buffering is happening. But because of the fact that this buffering helps in preventing the acidification or preventing the change in pH, these side chains of the imidazole side change of histidine is very important. But actually speaking, near 7.6, the buffering capacity is not as much as slightly below that. So probably 7 is where the buffering capacity is ending. So 5 to 7 is where it has maximum capacity. But again, what we need to keep is preventing an acidification. So you know that a lot of metabolites generate acidic products, and because of that the pH dips. So that is where the buffering capacity of histidine comes into play. I would also like to emphasize that it is not just histidine which is playing a role in the buffering capacity. There are so many other buffers which are coming into play. So it's a very complex system which actually helps in maintaining the pH of the blood or different body fluids. Okay. PKR, the R here is the side chain. Yes, please.
Sir, PI has no physiological significance, right? It is only for experimentation and that all.
I would not say experimentation, but don't confuse the PI with the buffering capacity. PI is the point at which there is electrical neutrality. So that is used in a different thing where you will be seeing that when you are separating amino acids, one of the properties by which it is separation happens is when the amino acid stops moving in a electrical field. So that is when it becomes neutral and it stops moving, and that is different from, and that differs from amino acid to amino acid. So all the amino acids will not stop moving in an electric field at the same point. So that is another way by which you can separate amino acids. So that will be discussed eventually. But yes, isoelectric point should not be confused with buffering capacity. So the glycine titration curve shows you that the buffering is not happening maximally at the isoelectric point. The buffering is because of the carboxyl group or the amino group or the side chain in cases of histidine. Okay?
Sir, one more question. Sir, so what is PK1?
Multiple people are having their one by one. Yes. So you can calculate
What is PK1?
PK1 is the pK value of the carboxyl group. So I told you that in glycine it is 2.3. In histidine it might not be 2.3, it might be slightly different, but it is in and around that range only. Okay. The pK value is not totally dependent on that group. It is also dependent on other factors. So that is why the pKa value changes slightly. It will not be identical in all amino acids. Okay. So I'll for today, since the class is ending at 12, I'll probably skip some of the slides at the end of this class and move on to a different topic. So since we had a 5-minute break, I think everybody will be fresh relatively. So I'll skip these slides and probably, let me just see if I can, okay. So can you see? No, I'm back. I have not left. Am I audible? And can you see the slide?
Yes, sir, we can see the slides.
So I've basically jumped onto a different class because I don't want to. I probably want to discuss another important thing and then move the slides which were remaining on to Thursday's class. Is that okay with everybody? I'll be talking about protein structure a little. Okay. So I'll cover the slides which I left on Thursday at 2 o'clock or on next Monday, and probably shuffle around a little and cover the important topics first before some other things which are relatively easy to understand. So we are starting off again, and we are talking about protein structure, peptide bond. So after some of these slides, you should be able to understand how amino acids join with each other and how the peptide bond is formed, and understand characteristics of the peptide bond and some classification of proteins, which again I'll probably skip or go through very quickly. And I would like to devote some time to the organizational level of protein structure and discuss protein structure and function eventually. So all of you had mentioned that how amino acids are linked to each other is through the peptide bond. Okay, so here note that I'm showing you two amino acids. So this is one amino acid on the left and another amino acid on the right. The central carbon, alpha carbon, and how the peptide bond is formed between the carboxyl group of one amino acid and the amino group of the next amino acid. So this is how the peptide bond is formed, and in the process of this covalent bond being formed, there is the release of one molecule of water. So here you can see two amino acids being linked together and the peptide bond being formed. So what can you see on face value is that one, it's a dehydration reaction, a molecule of water is released and a peptide bond is formed. Now something very interesting which probably you will appreciate, that it's a trans bond, you can see that the CO and the NH are on opposite sides. So that's why it's called a trans bond. The peptide bond, the peptide linkage is a trans configuration. And another thing is that by virtue of the electron sharing between this CO and the NH, this bond also behaves like a partial double bond. There is some amount of resonance, and because of the electron sharing, this peptide bond behaves like a partial double bond. It's not a single bond, it's not a double bond, but a partial double bond because of electron sharing between the CO and the NH. Okay. Now, some features of the peptide bond. As I said, it's a covalent bond between two amino acids. It forms between the carboxyl group of one and the amino group of the other. And when two amino acids come together, one peptide bond is formed. But when two amino acids are coming together, the nomenclature is that it's a dipeptide. Okay? So that is slightly confusing, that because you see that only one peptide bond is formed, but when this compound is known as a dipeptide. Okay, so don't get confused with that. Sorry, I just okay. So you have a dipeptide being formed. So again, coming back to the characteristics of a peptide bond. It's a condensation reaction. One molecule of water is released. It's a covalent bond. It's a planar bond. So you will understand when you go through books that there is some amount of spatial rotation which is allowed between these, the asymmetric carbon and the carbonyl group and the amino group, but between the peptide bond there is actually no rotation. It's quite a rigid bond and it's planar. So if you actually see it in 3 dimension, you will find that it's planar. It's not a 3D, there is no rotation. So there's some amount of rigidity is there in the peptide bond. It's a trans bond, as I said. So you can see that the groups are on opposite sides, and that is why it's called a trans bond. It's a partial double bond because of the electron sharing, and it's uncharged, does not allow ionization, and requires energy to form. So these are some characteristics of the peptide bond which you should keep in mind. It's a covalent bond, it's a planar bond, it's a trans bond, it's rigid, not free to rotate. So we'll be talking about rotation when we discuss something else. And it's a partial double bond by virtue of electron sharing between the CO and the NH groups, and it is uncharged, does not allow ionization, but it helps. So there is some amount of, and it requires energy to form. Yes, it's an endergonic reaction. Okay. Now again, this is something which I'll just quickly go over, not spend too much time. This is classic. Have you understood about the peptide bond? Is it clear?
So bond formation requires energy or releases energy?
It requires energy. It's an endergonic reaction. Okay. Now we are going into classification of proteins. These are again some things which are not very important, but you will come across these terms, so that is why it's important to we will discuss about that little later. So about classification of proteins, there are different ways to classify proteins. You are not expected to memorize all these classifications. Just know that there are classifications which exist. So you can have, based on the names or shape and size, you have elongated fibrous proteins like collagen and keratin, and you have globular proteins like hemoglobin and myoglobin. Again, on the basis of functional properties, you have defense proteins, contractile proteins, respiratory proteins, structural proteins, enzymes, hormones. So these are again different ways to classify. So you will come across these terminologies. So that is why I am just briefly explaining that there is classification of proteins on the basis of their functional properties. Okay. Now again, on the solubility and physical properties, you have simple proteins, conjugated proteins, derived proteins. So what are simple proteins? They are, again, as the name suggests, they are simple proteins on the basis of their solubility and heat coagulability. You have histone proteins, albumins, globulins, and other different types of proteins which are soluble, and based on their heat coagulability, they are grouped in simple proteins. And conjugated proteins again are something, as the name suggests, not only proteins but have some other groups associated with them. So if you have some proteins which mucopolysaccharides, some proteins with carbohydrate moieties, some have phosphoric acid, some have lipids, so you have lipoproteins, and metalloproteins containing zinc or iron. So these are again conjugated proteins, and as the name suggests, there are some other groups conjugated to the proteins. So these are commonly called as prosthetic groups and non-amino acid part of a conjugated protein. So you will be coming across these terms. That is why I am just briefly explaining these terms, that a non-amino acid part of a protein or a conjugated protein is maybe something like zinc or lipids. So you have, yes, any questions? It's a vitamin, but yes, it has got some amount of protein amino acid components in them also. So in the classical sense, it can't be called a protein, it's a vitamin. Okay, now we'll also be talking about multi-subunit proteins eventually when we discuss protein structure. And you know that all proteins may not be consisting of a single polypeptide chain. There might be, like in hemoglobin, you have different polypeptide chains. So there are multiple subunits, and that is called as a multi-subunit protein. And it can be oligomeric, and if the two units are identical, or if it is known as a protomer, or it can be a heteromer, depending on whether the subunits are similar or different. Okay, so I'm just walking through the classification very quickly because I want to come into the protein structure part. So again, these are not very important, but you can have books which discuss about these proteins, not very important, but there are again classifications which have proteins being subdivided into different categories based on their water solubility and heat coagulability. So these are also classifications. You don't have to memorize them, you just have to know that certain classifications exist. Now coming to protein structure, this is something which is important and which I would like all of you to pay attention to, is that there are different levels of organization of protein structure. When we talk about amino acids being linked to each other, that is essentially the primary structure. Okay, and above you can see that there is some nomenclature which is slightly different, that the difference between conformation and configuration. So this is again something which is given in Harper. You can see that this is not extremely important, but sometimes it can be confusing because there are similar sounding names, and if you remember the D and L forms, that is configuration, and conformation is where the spatial relationship. So essentially it is the same thing, but there is a slight difference in the sense that interconversion involves breaking of bonds if you are talking about configuration, and if you are talking about conformation, there is no breaking of bonds when it converts from one form to the other. Okay, this is not that important. I would like you to concentrate on the organizational levels of protein structure. So the primary structure is essentially the sequence of amino acids. Okay. What do you mean by secondary structure? Secondary structure is folding of short contiguous polypeptides into geometrically ordered units. So I'll show you the diagrams which will make things clearer. Then there comes into tertiary structure. So assembly of multiple secondary structural units into larger three-dimensional units is known as tertiary structure. And the tertiary structure is by which the protein gets its functional aspect. Okay, so remember that the tertiary structure is responsible for the protein function. That is extremely important. And quaternary structure is when you have number of polypeptides, and these polypeptides can come together as different subunits. Okay, so let us understand what is primary structure. So as I told you in the beginning, that you have an amino terminal and a carboxyl terminal. So when they are joined, there is sort of a polarity, or the nomenclature is followed where you go from amino to carboxyl end, and that is how the amino acids are linked together. So the sequence of amino acids linked with one another is known as the primary structure. Okay, I have a question here. So you have heard about denaturation of proteins. So what do you understand by denaturation of proteins? Chat box. Denaturation of proteins. Have you heard the term denaturation of proteins? Breaking of bonds. So will the primary structure be lost? No. Good. So the primary structure is conserved during denaturation of proteins. It's the tertiary structure which is disrupted, and because of denaturation of proteins, you will see that proteins lose their functional capacity. So we will be discussing denaturation of proteins eventually. Now primary structure is clear. So it is essentially how the amino acids are, the sequence of amino acids linked with one another, and see that it is in the polarity is followed. So the amino group comes first and the carboxyl group comes at the end, and the peptide bond, as we just discussed, is formed linking one amino acid to the other. So the primary structure of the protein is essentially the sequence of amino acids linked to one another through the peptide bond. Now, what do you mean by secondary structure? It is the localized folding of a polypeptide chain, and as many of you have mentioned that it forms helices or sheets. So one of the common forms is alpha helix and beta sheet. So these are localized, very localized folding of the polypeptide chain. So you can see the polypeptide chain here, but when it folds into chains called helices or sheets called beta sheets, and connecting between them there are turns or loops. So this is what it looks like. So when the sequence of amino acid folds into a chain or a helix, it's known as an alpha helix. And what is interesting is that the secondary structure is stabilized because of the hydrogen bonds formed between different amino acids. So just note that when there is secondary structure, there is a lot of hydrogen bonds involved. And another very interesting thing is that these hydrogen bonds by themselves, all the non-covalent interactions by themselves are much weaker compared to the covalent interactions. But because of their numbers, there are so many numbers of non-covalent bonds being formed. For example, the hydrogen bond, that they as a group lend a lot of stability to the secondary structure of the protein. Okay? Ultimately, it's the thermodynamic stability which decides the energy conformation, which decides which form it will take. But whichever form it takes, that form is stabilized. The structural form is stabilized through hydrogen bonds. Okay? Now, again, a little trivia about the alpha helix. So you can see how the alpha helix is formed. It's essentially, if you draw a transparent line through the center, you will have an axis at the center around which the amino acids are coiled in the form of a spring or in the form of a helix. Okay? And it can be a right-handed helix. So you remember your thumb rule from your school. It can be a right-handed helix or a left-handed helix, and the coiling will differ slightly from one another. And there are approximately 3.6 amino acids in one turn of this helix. Okay? So, and another very interesting thing which I pointed out is that you have hydrogen bonds stabilizing this structure, but there is also the fact that there are hydrophobic groups and hydrophilic groups. So generally it has been seen that hydrophobic groups have a tendency to come inside, towards the inside of this helix, and hydrophilic groups have a tendency to protrude outside. So when you look at it from the top, you will find hydrophilic groups protruding outside and hydrophobic groups or hydrophobic residues coming slightly inside of the helix. Okay? Though it is said that the R groups face outwards, but you can still differentiate between the hydrophobic and the hydrophilic by their tendency to go towards extreme outside or relatively inside. Okay? And another interesting thing is that because of the shape of proline and glycine, they are often found in only certain places of the helix. So because of its position or because of its amino group, it does not always allow the helix to form properly. So it can only accommodate within certain positions of the helix. And glycine, again, by virtue of its very small size, it can accommodate into very sharp bends of the helix. It is not found in all places. It can only be accommodated, proline and glycine can only be accommodated in only specific areas because of their physical properties of size. So again, size is something which will be discussed in today afternoon's class. So size of an amino acid also plays a role in helping separate amino acids. So whether it's a small amino acid or a big amino acid or a small protein or a big protein, you can use that property to separate one protein from the other or one amino acid from the other. So these are again physical properties which are determined by structure. So we talked about the alpha helix, which is a secondary structure. No, it's actually the right-handed helix is more stable. I actually don't know the answer to that because it's actually determined by not only the structural aspect but also the thermodynamic stability. So the ultimate decider of or the structure will be the thermodynamic stability of the structure. But yes, it has been observed, it has been found that a right-handed alpha helix is more stable. So maybe if you can find the reason, you can share that with me, because I haven't found in any of the books the reason for why a right-handed helix is more stable than a left-handed helix. Okay. So is this clear? Can we move forward? Any questions about the alpha helix? Any questions about the alpha helix? Can we move to the beta sheet? So this is just a secondary structure, helix, like a spring. So when you talk about a transmembrane protein, it is, you will be talking about the full protein. So we haven't completed the structure of a protein as yet. So you'll realize the complexity when you go to the tertiary and the quaternary structure. So wait a little. So this is another form, a very common form of secondary structure is the beta pleated sheet or the beta sheet. And as the name suggests, it resembles a sheet. So you can see the diagram that the arrangement of the amino acids resembles a sheet. So it's a zigzag pattern and it's a pleated pattern. So the backbone is actually arranged in such a way that the R groups are actually pointing away from each other. They are opposite to each other compared to the alpha helix which they were protruding out. Here they are pointing opposite to each other. And again, the stability of the beta helix, you can see the hydrogen bonds, multiple hydrogen bonds contributing to the stability of this secondary structure, the beta pleated sheet. And another very interesting observation which has been seen is that it can be parallel or anti-parallel. So you can have, as I said, there is a polarity and a direction to the amino acid chain. So if the direction of these chains is parallel, then it is known as a parallel conformation and can also be anti-parallel. So it can be anti-parallel or parallel as the sheet forms or as the polypeptides arrange themselves. And you can see the multiple hydrogen bonds stabilizing this beta pleated sheet, this beta pleated sheet structure. So it's a very interesting conformation, and this is the second level of organization, the secondary structure of a protein. Is this clear to all of you? The beta pleated sheet. Now, obviously, it is not limited to secondary structures, and secondary structures are, so parallel, anti-parallel is basically, somebody asked me what is parallel and anti-parallel. So what I told you at the beginning is that when you start naming or when you start nomenclature of a polypeptide, it is from amino terminal to carboxyl terminal. So if the arrangement of the sheet or the polypeptide chain is the same direction, then it is called parallel. And if it is in the opposite direction, so if two polypeptide chains are lined opposite to each other in the polarity, then it will be called as anti-parallel. Okay, so you can see the nomenclature, the direction of the arrow pointing towards the same direction or in opposite direction, it is called as anti-parallel. Now there are also turns and bends or loops which are associated with these secondary structures, linking one secondary structure to the other. So these are called as super secondary structure or motifs. Okay, so these are again loops and turns which are binding one secondary structure to the other. So motif is a slightly complicated definition. If you see what, so somebody commonly asks that will the line of amino acids end at the ends? No, generally it's when you see the amino acids being formed as a sheet. So this is how they are arranged, and it's not a bending which is seen, but when you see the end, it is probably a link which is joining the two anti-parallel chains, and this is how they are linked. So there is no bending here, but the polypeptide chains are arranged in a sheet pattern and the hydrogen bond stabilizing them, and they may be in the same direction or in the opposite direction, parallel and anti-parallel.
Sir, are they different chains or what?
Yes, there are two different chains arranged in the form of a sheet.
Sir, but if there are more than two polypeptide chains, then won't it be the quaternary structure?
No. So here what you see is that the same chain which is existing, and they are linked to one another, but it's part of the same polypeptide chains. It's not a different chain altogether. Okay, so there are amino acids linking this part with another part. So here you can have this polypeptide chain existing like this, and there is a link between these two. Okay, so this is how the polypeptide chain is.
There is only one polypeptide chain, the entire one, which I'm in front of me. Fine, sir. Fine, thank you.
Okay. No, disulfide bonds are not commonly present in secondary structures, so I'll be coming to disulfide bonds eventually. So, super secondary structure loops, turns and bends help in linking different secondary structures. Now, coming to tertiary structure of a protein. So, we talked about what is a secondary structure? It's basically a localized folding of a polypeptide chain. It's a localized folding, and when you have these localized foldings, so only if the central circle is one beta sheet. Remember, this is a ribbon diagram. So this is just an alpha helix, and you have a linking these. So it can be a helix linked to a chain and things like linked to a sheet and things like that. Okay. Now, when you come to, so I'll be coming to motifs again. Now, tertiary structure, when we talk about tertiary structure, it's the complete folding of a polypeptide chain to form a 3D structure. It involves multiple secondary structures. So it's what we were talking about till now were small units of localized folding, and when we bring together multiple such subunits, you will have a tertiary structure. So the complete folding of a polypeptide chain to form a 3D structure will be the tertiary structure. And what is interesting is that it's not random. Every time it occurs, it will be in the same pattern, and it is specific, and the protein folding will happen the same way every time, and the protein which is formed is usually called it's a native protein. Okay, so remember this name, you might come across this name at some point of time, a native protein. So when this protein is formed, it will be formed in the same way, and it will form the same structure or the same spatial configuration or the same 3D structure every time it is formed, and it will be the native protein which is formed. It might change, but essentially also leads to formation of functional units called domains. Okay, so this is one of the characteristic features of the tertiary structure, in that it helps in forming functional unit called the domain, which is responsible for the function of a particular protein. So remember, we talked about different proteins having different functions. So the three-dimensional structure or the tertiary structure of the protein is actually responsible for the specific function of a protein. And again, to re-emphasize, the hydrophobic residues generally have a tendency to go towards the interior of this three-D structure, and the hydrophilic residues have a tendency to form on the outside. And as we were talking about hydrogen bonds playing an important role in stabilizing secondary structure, tertiary structure is stabilized by hydrogen bonds, disulfide bonds, hydrophobic interactions, ionic bonds, and van der Waals interactions. So because of the complex three-dimensional structure, a lot of other non-covalent bonds, disulfide bonds are obviously covalent bonds, but other than that, most of the other bonds are non-covalent bonds. Hydrogen bonds, hydrophobic interactions, ionic bonds, van der Waals interactions, all these bonds, even though they are very weak bonds, but collectively there are multiple such non-covalent bonds which help in stabilizing the total three-dimensional tertiary structure of a protein. Is this clear to everybody? Secondary structure and tertiary structure. So the difference between the two, and that tertiary structure is essentially responsible for formation of domains which are responsible for the function of a specific protein. So most of the covalent bonds are much more stronger than the non-covalent bonds. We talked about the peptide bonds as one of the strongest covalent bonds. Disulfide bonds are obviously stronger than the non-covalent bonds, but the non-covalent bonds get their importance from the multitude. So the large number of weak non-covalent bonds are responsible for stabilizing the tertiary structure. Now coming to motif and domain. So these terms might sound a little confusing at the beginning. So motifs are essentially short segments of 3D structure, like a helix turn helix, or a tertiary or a super secondary structure, which is commonly called. It may or may not be associated with a chemical or a biological function, but domains are essentially regions of a protein which are formed with a specific function. For example, you have a DNA binding domain, you have catalytic domains, you have regulatory domains, you have other domains which are calcium binding domains. So these are functional units which are formed as a result of the tertiary structure of the protein. So here you can see that this is how the tertiary structure is formed. And you have beta sheets. So this is one beta sheet, and within these beta sheets you have interconnection, you have alpha helices, and ionic bonds are not as strong as the peptide bonds, but yes, probably stronger than the non-covalent bonds. Other non-covalent bonds, I think the hydrophobic interactions are the weakest, even weaker than the hydrogen bonds. I'm actually not very sure about the quantitative difference in the strength of the hydrogen bonds or hydrophobic bonds. Ionic bonds are basically formed by sharing of electrons and salt bridges. You will come to them when you study hemoglobin and things like that. Okay, so now coming to quaternary structure. Now, slight difference. We were talking about polypeptide chains. So a quaternary structure essentially arises when a protein comprises of multiple polypeptide chains. So you have multiple polypeptide chains coming together polypeptide chain will not have or will not result in a quaternary structure. It needs to have multiple subunits which may be similar or dissimilar to form dimers or oligomers or protomers, and it will be coming together to form a quaternary structure. And these polypeptide chains are not covalently bound, but they have electrostatic interactions which link one to the other, and like tertiary structure, quaternary structure is also stabilized by non-covalent bonds. Okay? So you have, now this will tell you the difference. So you have, this is the primary structure and one amino acid is linked to the other, and this forms the secondary structure which folds amongst itself to form the tertiary structure, the functional unit, and multiple subunits might come together to form the quaternary structure. So this is the sequence of a chain of amino acids. Then the secondary structure, either a helical or a beta-pleated sheet, the localized folding of polypeptide chains, and the tertiary protein which brings together multiple such secondary structures and forming a three-dimensional folding pattern, and ultimately the quaternary structure. Okay, so this is how the structural complexity of proteins is explained. Is this clear to everybody? If you have any doubts or if you have any questions regarding primary, secondary, tertiary or quaternary structure, please ask. Anybody has any questions regarding these structures? Okay, so we'll discuss domains. Okay, I'll just explain domains once again. So you saw that the secondary structures are formed in the form of alpha helix and a beta-pleated sheet. Okay, yeah, I'll just explain native protein also. Yes, so I'll just explain some of the areas which are a little confusing. So once you have a secondary structure which is formed, you know that this is a primary structure, and then it folds upon itself to form localized folding to form a chain or a sheet, the beta sheet or the alpha helix, that forms the secondary structure which is stabilized by multiple hydrogen bonds. Okay, now these are forming, and when multiple secondary structures are linked to one another, they help in forming the three-dimensional structure of the whole polypeptide. Now this polypeptide folding, this three-dimensional folding leads to a functional protein which is the same every time. So every time a protein is synthesized, it will always fold into the same structure, unless obviously there is some problem in the protein folding, and that three-dimensional folding which will actually bring about the functional specificity of the protein. Okay, and that is known as the native protein. So the functionally folded three-dimensional structure which is formed when proteins are synthesized are known as native proteins. Okay, and when these three-dimensional structures form, they form domains, or which are the functional units. As these three-dimensional structures come together, they form small areas which give the functional specificity to the protein. So you have calcium binding domains, you have catalytic domains. Is every domain a motif? Okay, so let me explain. So motif, the difference between a motif and a domain is often confusing. So a motif is a short segment of 3D structure. It may or may not lead to a domain. Usually a domain is more complex. Motif is more simpler helix turn helix or a helix loop helix. So that forms a motif. It's a short segment of three-dimensional structure. It may or may not form a domain. Domain is more complicated. It's a more complex structure, but remember that the domain is not the total 3D structure. Within a 3D structure, you have smaller functional subunits which are called as domains. But because of these functional subunits, the protein gets its specific function. So you can have a DNA binding domain which gives the functional specificity to a protein, and a catalytic domain, a regulatory domain, a hydrophobic domain. So there are different domains which give the functional specificity. A motif compared to a domain is a simpler or a shorter segment of a three-dimensional structure. Yes, a motif is a much smaller dimension in the whole protein folding. A domain is a larger, so as to say, functional unit. Okay, is that clear? So I'll end here. So there is a very interesting question: is the domain equal to an active site? So when you talk about active site of an enzyme, it is a catalytic domain, but it is not all domains are catalytic domains. You might have DNA binding domains, you might have calcium binding domains, you might have regulatory domains. So there are different domains which are formed, but yes, the catalytic domain is basically the active site is the catalytic domain, which is only part of the three-dimensional structure of a full protein. Yes. Okay. So I'll leave it here. I have not completed all the slides. I'll finish here today, and we'll probably start from whatever is left of the first class and the second class. I actually wanted to cover a full segment rather than leaving it halfway through. So that is why I covered these two segments partially. So we'll come back to, there are some things which have left. Okay, I'll share the slides. These are all given in books. I have not actually written something de novo, but yes, I'll share the slides. I would also probably like you to give you some reference books which you can go through. Harper is very dense, so you can refer to Harper, but a lot of things which we discussed today are probably not given in very much detail in Harper, but there are a lot of interesting and newer things which have been discussed in Harper. Today afternoon, Dr. Asta will also be discussing about protein fractionation, and that will be how you utilize properties of proteins which we discussed in today's class. So whether it is size or charge or other properties which can be used to discuss, which can be used to separate out proteins, protein fractionation. So that will be a very interesting class. Please attend today's class in the afternoon. That will be another very interesting class. And we'll again connect on Thursday. I have a class at 2 p.m. and we'll discuss about some of the things which we left off and other important things which will be of importance to you. Okay, and please read up, and if you have any doubts, we can discuss on Thursday or next Monday. Thank you. Any questions, please put it up on the chat box if you have any questions left. So both my classes are incomplete, even though I had 2 classes, 2 hours, but I still have 2 classes which are incomplete, but I tried to cover some areas which are important and which I felt will be slightly confusing when you start going through the book. So when you go through the books, you will find that these become easier. Okay? Yeah, I'll upload that. Motif and a domain. Okay, that doubt will still remain. Okay, thank you. Thank you.
histidine perform the buffering action even when it is in the form of protein, that is even after forming peptide bond, because its buffering action is due to.
Hello?
Yes, sir.
Yeah. So
The histidine will perform its buffering action.
yeah, histidine will be there in a lot of
अभी दूसरा क्लास नहीं है 12 बजे से? 12 बजे से दूसरा क्लास नहीं है?
नहीं हो गया सर का, हो गया खत्म?
सर का खत्म हो गया, सब छोड़ रहे हैं।
make